have here a wood block at rest on a tabletop, and even if the tabletop appears very smooth and the wood block has been sanded to be very smooth, nevertheless, if you zoom way in at this region where the underside of the wood block is in contact with the surface, if you zoom way in, you'll see that the wood surface is actually quite rugged here, and the tabletop surface is very rugged as well. It'll appear like you've got two interlocking mountainous landscapes down here on the nanoscale. Friction is the result of this weak intermolecular bonding between the atoms of the two surfaces in contact. The atoms interact attractively with each other when they come within nanometers of each other, and exert micro forces to resist being pulled apart. So if you push on the wood block, kind of shifting those wood atoms to the right, you're stretching out those intermolecular bonds, each of which acts like a little spring trying to pull the wood atoms back to the left. Likewise, all these surface atoms are going to be pulled to the right by these stretched out bonds as the wood block tries to sort of drag the surface along with it to the right. If the wood block actually starts to move, these bonds will be stretched so far that they'll eventually break and release energy in the form of heat, heating up the two surfaces in contact. And you know you get heat whenever you have friction. So then the net result here of all these microscopic interactions as you try and push the surfaces parallel to each other will be a net macroscopic force to the left on the wood and to the right on the surface. This component of the contact force parallel to the surfaces we call, of course, the force of friction. So there'll be a force of friction to the left on the wood block and also a force of friction to the right on the surface as the block tries to drag the surface along with it. This is obviously a very complicated process, so we need a mathematical model for friction that simplifies all these interactions but still makes accurate predictions. Enter the Coulomb model for dry friction. Named after Charles Augustin de Coulomb here, who we shall encounter again when we come back around to study electric forces. The Coulomb model for dry friction. The model has a couple of limitations. It does not accurately model wet friction, hence the word dry right here. So this doesn't really give a good description for lubricated surfaces or conjoined surfaces, like if there's Velcro or an adhesive between them. We would need different physics to model these sorts of things. But for two dry surfaces, this Coulomb model does pretty well at making mathematical predictions for how friction will behave. It has two key features. First key feature of the Coulomb model for dry friction. The strength of the friction depends on the combination of surface materials. That is, what they're made of and what their textures are like on the macro scale and their microscopic texture as well. The combination of materials matters. So wood on stone will behave differently friction-wise than wood on steel. Property number two, feature number two. The two components of the contact force between the two surfaces, the components of the contact force, the parallel and perpendicular components, are linked. The size of the parallel component, that's the friction, so the size of the friction depends on the size of the perpendicular component of the contact force. That's the normal force. The size of friction depends on the size of the normal force. The normal force represents how hard the surfaces are pressing into each other. And so the harder they press into each other, the stronger the friction between them can be. That's the second key feature of this Coulomb model of dry friction. Let's examine this feature of the model by talking for a moment about pressure. You may know that air pressure in car tires is often measured in units called PSI, which stands for pounds per square inch. That unit actually tells you how pressure is defined. Since a pound is a unit of force and a square inch is a unit of surface area, pounds per square inch indicates that the pressure exerted on a surface is defined as force per unit area. In other words, to find the pressure exerted on a surface, take the magnitude of the normal force pushing on the surface and divide by the area of the surface. And put another way, the strength of the normal force exerted on a surface is equal to the pressure at the surface times the area of the surface. So higher pressure exerted over a larger surface results in greater normal force. Here's an illustration of how normal force, surface area, and pressure are related. Imagine standing on thin ice over a pond. The normal force the ice exerts on you is equal to your weight, but that force is spread out over the bottoms of your 2 feet. So the pressure you exert on the ice is equal to your weight divided by the small surface area of your 2 footprints. That large pressure could be enough to break the ice. So on thin ice, it's advisable to lie down on your belly and spread your weight out. The normal force the ice exerts on you is still equal to your weight, same normal force in both cases, equal to your weight, but now it's spread out over a larger surface area, resulting in a much smaller pressure on the ice. A smaller pressure means the ice is much less likely to break.